بسم الله الرحمن الرحيم. أول شيء we'll talk about the partial differentiation with the degrees. Okay, so partial x to the power n. This means that if you have a function of x, y, z, etc., and you're asked to do a partial differentiation, and let's set, for example, n is equal to 1. Okay, this means that you'll do a differentiation only to the respect to this variable. Any other variable will be just counted as constants, like any number, 1, 2, 3, whatever. So let's say you have 3 f is equal to 3yx squared over z. To differentiate this, let's say partial f over partial x. You will count as all of these as constants, and you only differentiate on this. You just operate on the x square. So you will be having 3y 2x over z equal to 6yx over z. You can do the same thing over any other variable. Let's say y, you'll be having 3x squared over z. The same thing can happen on partial f over partial z to be equal to negative 3yx squared over z squared. Do you know how we got this? We know that the differentiation of any function f of x is equal to negative the derivative over the actual function squared. Just to remember. Okay, now we can use a higher degree or a higher form of partial differentiation. Let's say partial square f over partial x squared. Just a minute, please. Okay, sorry. Okay, now let's do this. This number 2 means that you will operate or you differentiate twice for the same function. So the first time we'll have partial x of this one to be it will be 6yx over z. Now we need to do partial differentiation again for this one. So you will have partial square f partial x squared is equal to 6y over z. Okay, that's the basic concept. Now what if you have partial square f over partial x partial y? It means that you will do partial differentiation twice, once for x, the second one for y. But it doesn't matter that if you started with x or y, because this is also equal to partial square f or partial y partial x. It's the same. You can start with any variable you want. Okay, so let's say that you want to do it for this, the same function. You will start with an x. So you'll have 6yx over z. Then you'll do the partial differentiation again for the respective y. This one is partial x. Now, as for partial y, you will have 6x over z. Okay? You understand this? Okay, we can represent this as the following: partial f over partial x. We can represent it in a different form, which is f with a subscript x. Same thing for y, same thing for z, same thing for any variable. If you have For example, this it can be represented by this form or this form. It's the same thing. Okay, let's have another example on this, but let's use a complex form. F equals to xy cosine z plus e to the power xy z. Okay, let's find partial f over partial x. You'll count these as constants and these also as constants for the first, sorry, for this differentiation. So you'll have y cosine z plus y z e to the power xyz. You can do this for any other variable, let's say partial f over partial z. You'll be having negative xy sine z plus xy e to the power z. Is this clear?
Yes, it's clear.
Okay, do you have any other example that you want me to work on? This is a similar example. Okay, let's try chain rule. Chain rule and breaking functions. Okay, let's have a complicated function like this. Okay, and you are asked to find its derivative. Can you differentiate it with the old methods that you used in calculus 1 and 2? You can, but it will be very tedious for you. Okay, so what you're going to do is to make this function much easier. Start with the smaller functions. Okay, let's set z is equal to x squared, which is this. So we'll have cosine square z. And you can set cosine square z to another variable. Let's say y is equal to cosine square y. Okay? So you can have the following. Or you can also simplify it furthermore. You can have w is equal to ln square y. Okay? So eventually f is equal to w. Something simple, right? Now we will have to do what's called partial derivative. Just find the partial derivative of each of them. So, or just the derivative. dz over dx, you'll get 2x dy over, sorry, this is z. Okay. dy over dz, you will have 2 cosine z. Here's a negative sine z. And dw dy. You'll have 2 ln y over y. All right. Now, for df dx, it's equal to the multiplication of all these terms. So we'll get 2x negative 2 cosine z sine z 2 ln y over y. Now you need to just expand it and substitute the old values, the xy, sorry, the yz or any other term you have. So just gather up the multiplications. You will have negative 8 x, because this is the simplest form as for x. So, and for cosine z and sine z, what z is equal to? Cosine x squared sine x squared multiplied with ln y. Ln y is equal to cosine square x squared, right? Cosine squared x squared over y. Y is equal to x cosine squared x squared. Okay, cosine squared x squared. Now all you need to is just to simplify this. Simplifying this, you get remove the power from here, cancel this, and you'll have negative 8x sine x squared ln cosine x squared. Anyway, you can see that this term can be simplified to tan. So you'll have negative 8x tan x squared ln cosine squared x squared. That's the answer for your question. Okay, that's df dx. You can try this by your own or create your own questions. Just go create it, okay? That question was actually called chain rule. That's chain rule and breaking functions. Now there's another form of chain rule. I want you to find, let's say not dz. I want you to find dz dx and dz dy. Okay? Or what's better, to find dz du and dz dv. There are many methods to find this. The first one, which is called substitution, you just substitute the values in the function, then operate your differentiation, which I don't recommend because it's going to be very long. You can go with chain rule. So the chain rule is, if you have, let's say, dz du, it's going to be equal to, look at these variables, partial z over partial x multiplied with their derivatives, partial x over partial u, plus partial z over partial y multiplied with partial y over partial u. Okay, now to make things easier and less messy, you can find these here in a different side of your paper or whatever. So you will have partial z over partial x, it's equal to 2x. Partial z, partial y, it's all going to be equal to 2y. Partial x over partial u is going to be equal to 2u. Partial y over partial u is going to be equal to v. Now just substitute. Partial z over partial x is equal to 2x multiplied with partial x partial u, which is equal to 2u, plus partial z over partial y, it's equal to 2y, partial u over partial y, so partial y over partial u, it's equal to v. Simplify, 4x u plus 2yv. Now let's do the same for dz dv. Let's find dz dv. Now we need to find few new terms. These will no longer be needed. So we use partial x over partial v. It's going to be negative v. Partial y over partial v, it's equal to u. We'll use the same method. Partial z over partial x multiplied with partial x over partial v plus partial z over partial y multiplied with partial y over partial v. Okay, now just substitute what you have here. So we have 2x multiplied with negative 2v plus 2y multiplied with u. So you'll have negative 4xv plus 2yu. Okay, you can see it's just multiplying and substitution is very easy. Okay, what if you have something called total differentiation? Total differentiation is another type of chain rule. Maybe you can find it's much easier than this. Maybe you'll find it more difficult. Personally, I find this method is easier, but you can use whatever you want or whatever is needed in the exam. Just give me a minute. Okay. Total differentiation. You're having the same question, just to understand the concept. Okay, we need to find partial z over partial x, which is going to be equal to 2x. Partial z over partial y is equal to 2y. Now, what we have here is that we want dz. dz. The formula of dz is basically partial z over partial x multiplied with dx plus partial z over partial y multiplied with dy. Okay, just substitute the values here. You get 2x dx plus 2y dy. Okay, what about these two? What you're going to do is basically just derive them from the given functions here. Okay, what you have here is dx. What's dx? It's equal to 2u du minus 2v dv. And as for y, you have chain rule because you have a multiplication. So dy is going to be equal u dv plus v du. This seems familiar, right, from differential equations. Okay, now substitute these values and this. Okay, we'll get 2x. That's the dx. Okay, 2x, 2u du minus 2v dv plus 2y dy is equal to u dv. Just let me check. Yeah, okay. dv plus v du. Okay. Now just simplify this. You will have 4x u du minus 4xv dv plus 2yu dv plus 2v plus 2vy du. You just gather up the values with the dy on a side and the dv on a side. You will get 4xu and 2vy du plus negative 4xv plus 2yu dv. This all is equal to dz. Now I want you to compare these values with this problem that we solved earlier. You can see they're the same, but we got them in two different steps. Got them in two different steps. So you got these values from here, and you were asked, let's say, to find dz over du. dz over du. We have a du here. You cancel this. Okay, you cancel this. That's your value here. 4x u plus 2v y. That's your value. Compare it with the question that we solved before. You'll find it the same. dz du, it's the same. Okay, exactly the same. The same thing if you're asked to find dz over dv. You cancel this, you keep this one. You'll get the same answer that we did before. Okay, clear so far?
Yes, it's clear.
Okay, Now to optimization. Just to check with your syllabus, is there anything else? You can work on these problems. Okay, there's Taylor series. Yes, there's Taylor series. Let's do a problem on Taylor series. Okay, just a minute. Okay, that's your question. We'll work on this question. I think that you solved the question with sine with the doctor. We'll do something here with the cosine. So you're given a function of cosine x, and you're required to approximate f at 0.01. Okay, now what you want to do here is to find approximated answer. So what's the famous function that you know that's close to this and can solve f cosine x? Personally, I find f of 0 is famous because cosine 0 is equal to 1, correct? Okay, so using this value and this value, you can find what's called delta x. Okay, delta x. So it's 0 minus 0.01 minus 0. It's the same 0.01. That's your delta x. Okay, and the value 0 is called your x naught. It's equal to 0. Now, all you need to do is just apply Taylor series. Let's make it simple, and you're only required to find the first 3 differentiations or iterations or whatever. So you'll have f of x, it's equal to cosine x. You need to find the derivative. It's equal to negative sine x. Its derivative again, which is double prime, you will get negative cosine x. Okay. Now, you need to apply Taylor series. F of x is almost equal, approximated to f x at 0 plus f prime x at 0 or x naught delta x over 1. I don't know what this is called. Okay. Plus f double prime x naught delta x to exclamation mark, etc. Okay. Now just substitute. So fx at 0, which is cosine 0 plus f prime, it's a negative, sine 0 delta x 0.01, okay, over 1, and this is going to be negative cosine 0 delta x 0.01 square over 2. Okay, now simplify it. Cosine 0 is equal to 1. Sine 0 multiplied something, it's still a 0. Minus 1 multiplied with 0.01, which is going to be 0.001 over 2. This is equal to 1 minus 0.0005. This is equal only to 0.9995. Correct? Yes, that's the answer. So approximately cosine 0.01 is approximately equal to 0.9995. Okay, that's the Taylor series for this. You can check with your calculator later, but this is the method to use. You can use furthermore differentiations. What, let's say they're just asked for the first two or maybe the first three. That's it. That's for simplification. Okay. You go to optimization.